Monica, is the recording on?
A very good morning, good evening, good afternoon to all our members and our friends in IEEE Region 10 and all around the world. Um, I'm Varunika Hippala. I'm the student representative of IEEE Region 10 and I will be your host for the day. So you are joining and witnessing the IEEE Region 10 talk number 40. IEEE Region 10 Talk is a joint initiative by IEEE Region 10 committees led by IEEE Region 10 Professional Activities Committee. And today we remark the 14th episode of IEEE Region 10 Talk. And here in IEEE Region 10 Talk or R10 Talk, we discuss key technical and non-technical aspects with renowned speakers all over the world. And so as today, so we have a interesting and very important uh, agenda coming up. So before we moving on to the session, let me go through a little information, a little things on how this is conducted. Now, so first, we will be welcoming you all from IEEE Region 10, and the session will start. And if you have any questions or any issues, if you want to ask anything from the speaker, you can use the chat box here. Right. So with that, without further ado, let me introduce our who will welcome you today. So let me invite Professor Cook Jin Chun, the past director of IEEE Region 10, to welcome you all and to introduce the speaker and invite him for the session of IEEE Region 10 Talk 40. Professor Cook Jin, over to you.
Hello, everyone. This is my great honor and pleasure to introduce our esteemed speaker today. First of all, most modern pianos have a row of 88 black and white keys. So today we'll have a very interesting topic with the piano and the engineering and the related science. Then is the piano a percussion instrument or a stringed instrument or a keyboard instrument? So you'll find out the answer in this talk. And this presentation will explore some of the main aspects of the design compromises and developments that have been implemented in all commercial piano designs since the late 19th century. The focus will be particularly upon the scientific details of sound production of pianos and how pianos have been engineered to exploit the principles of acoustics, dispelling some common misconceptions along the way. We are very fortunate to have Dr. Clive Woods, Professor Clive Woods, actually, today as a speaker. His biography is in the announcement so that you can take a look, but if I introduce some of his excellent achievements so far, then he studied at the New College in the University of Oxford, where he earned bachelor's degree, master's degree, and the Doctor of Philosophy degree. He worked at several different institutions, including Plessy Research, University of Sheffield in UK, and Iowa State University in USA. Now he's with the University of South Alabama from 2016 as an Associate Dean of Engineering. He also collaborated closely with Region 10 people. In 2010, he was appointed Japan Program Director at the NSF, National Science Foundation of USA, and subsequently to additional responsibility for the US collaborative basic research programs in Korea, New Zealand, Australia, Mongolia, and Taiwan. And he received the NSF Director's Award and the Doctor of Science Higher Doctorate by the University of Oxford in 2015, acknowledging his distinguished research achievements over many years. He's an IT fellow and a member of the editorial board of IEEE Nanodielectrics and Springer Nature Light Science and Applications. IEEE appointed him to its Ethics and Member Conduct Committee, where he chaired in 2022 and 2023 this year. Finally, he's an accomplished pianist. He has played at many public concerts in both Europe and North America, including France, Germany, New York, Washington, D.C., Maryland, England, and London. He's particularly well known as a soloist, as an accompanist for operatic and choral works. So, Dr. Clive Woods, now you're on.
Okay, well, thank you very much indeed for that introduction, and also thank you very much indeed for inviting me to give this talk. It's a subject that obviously is very close to my heart. I've been a pianist all my life. I can't remember a time when I wasn't fascinated by pianos, and I guess my interest in how pianos work was spurred by the fact that my music teachers were often telling me things that it sounded to me like were impossible, and I knew were impossible from my studies of science. It took me a long time to fathom out why they were saying what they were saying and what they really meant. Perhaps they weren't wrong after all, but you have to interpret what music teachers say in a particular way. So I'm going to start sharing my slides here. And so there we go. There's my first slide. So as you see, I'm at the University of South Alabama. This is in Mobile on the Gulf Coast of the United States, and there's a picture of me in an earlier age when I had a little bit more hair, and when I was going around playing lots of concerts, perhaps more than I do right now. I should make clear that everything I'm going to show you is, or at least most of it, if not all, is all well known to the top piano manufacturers. I'm not claiming any novelty in any of this, but it's really presented. I'm going to try and present it in a way that perhaps musicians won't have seen before, and perhaps technology experts won't have seen before. So here's a summary of what I'm going to talk about. This is actually a huge topic, and I'm really only going to be able to skim the surface, and even the topics that I choose just arbitrarily, I can't go into fine detail. There are people, particularly in the top active manufacturers, in the research departments of the very best manufacturers, who go into all this in very great detail, which I can't, obviously, in a very general talk like this. There are several topics that I regret I'm just not going to be able to touch at all. For example, the mechanism of a piano. There's the mechanism of a grand piano. It's actually or the action, as we call it, is actually a very, very clever mechanism. A lot of thought has gone into that from a lot of people, and its operation is really very subtle indeed, and one could do an entire talk on how that mechanism works and still not cover everything that there is to know about it. And there are still innovations being made in piano mechanisms. So it's not a dead subject by any means. I'm not going to have time to talk about the pedals on a piano. You probably all know every grand piano has 3 pedals. They have special names. There's the broken pedal, the wrongly adjusted pedal, and the squeaky pedal. I don't have time to talk about that, but again, there are innovations even being made to those. The middle pedal in particular has a very subtle mechanism, very clever mechanism that the top manufacturers are still improving. Nor will I have time to talk about the wooden frame. You see there the woodwork that goes into a concert grand piano, and how the way that that's constructed, and the way that that is produced so that it can withstand all the stresses and strains of a piano. And that is an engineering marvel in itself. Very fine example of wood engineering. So I'm making no apology. I'm really just choosing arbitrary topics here, but mainly about how a piano sounds and how we make it sound the way that a modern piano sounds. So let's talk about some basics first of all. You probably all know that an octave consists of the distance between covered by 7 white keys from C to the C that's 7 white notes higher, or G to the next G that's 7 white notes higher, or the same distance between black keys. And musicians start counting from 1. Engineers tend to start counting from 0. So musicians call that an eighth or an octave. That's where the word octave comes from, of course. And everybody knows that an octave means that we double in the frequency. By the time I've finished, you'll even be doubting that, I'm afraid. So you can't take anything for granted in pianos. Anyway, supposedly an octave means that we double the frequency. And a semitone, I'm going to, I think probably in region 10, you probably use the British nomenclature that a semitone is the interval between any 2 adjacent keys. The US term is a half step. So if you're more familiar with the term half step, when I say semitone, I mean a half step. And in the modern era, all the semitones, every adjacent key and the one next, every key and the one next to it, the 2 adjacent keys, they all have the same frequency ratio. So you can count them on the keyboard above. There are 12 semitones per octave, so you can work out the way that has to work. Each semitone must have a frequency ratio from, say, C to C sharp, or F to F sharp, or G sharp to A. That frequency ratio is always the 12th root of 2, and you can easily work that out to be 5.9%. So every semitone is almost 6% higher in frequency than the note below. And then let me remind you what we mean by beats. If I take 2 pure sine waves and they go through something that is non-linear, and it must be non-linear, then what you get out of a nonlinear device is those 2 same sine waves, but also you get another frequency, the difference between the 2 frequencies that you put in. You also get the sum frequency out as well, but we don't worry about that. And the easiest way to demonstrate that, if you're not familiar with that, is if you whistle a constant note and then have somebody next to you who's whistling a slightly different note, you will hear the beat frequency very clearly in your head, because the human ear is non-linear. And those of you who know about radio design will know that on the front end of every radio set there's a mixer circuit that takes the broadcast signal and mixes it with an internal signal, and that mixer stage is non-linear, because what you want to get out of that is the difference frequency, or what they call the intermediate frequency in radio terms. Whenever we have 2 frequencies that are slightly different, listening to them with the human ear is in the context of this talk, then what you hear is another signal at their difference. The difference frequency. So let's think about keyboards and recall all semitones are supposed to be equal, and they have equal frequency ratios. And what that means, of course, is that inside a piano all the notes are equally spaced. And I didn't realize until very recently that there's a fundamental problem with keyboard design. As soon as you say that, just think about it. Supposing I call the width of the front of a white note W, and then let's look at the bottom three white notes on that keyboard, C, D, E, and that has a width of 3W, and if you count the note widths, the key widths at the back, that's 5 widths of keys at the back. So therefore the rear width of each of those notes is 3/5 of W. But now look at F, G, A, B. There are 4 white notes, so a total width of 4W, but there are 7 rear widths at the back of the keyboard. So the rear width for those notes is 4/7 of W, and that's slightly smaller. Unless you've done that calculation, I really would doubt that you would realize that by looking at a piano keyboard. The problem is, of course, that the mechanism inside has all the individual notes equally spaced, and yet coming off the keyboard, the key widths at the back are not equally spaced. So the manufacturers have to disguise that difference very subtly. I have 2 pianos at home. One is Japanese and one is European, and the keyboards look very subtly different, and the reason is that the manufacturers have disguised that difference in the rear widths in 2 rather different ways, and it gives the keyboard a rather different feel and a rather different look. Although when you're playing it, you hardly really notice it, except for noticing that the keyboards look a little bit different. Well, the people who draw keyboard diagrams on the internet have noticed that, and here I've got some keyboard diagrams from the internet, and also I have got 3 commercial objects that have keyboards printed on them, and you can see that really that problem has defeated the artists on the internet and the artists on the mug and the mouse mat and the beer coaster. They really didn't know how to cope with that problem, and most commercial pianos disguise this problem with the keyboard rather better than those. But let's think about something a little bit more technical on keyboards. And again, this arises from all the semitones are supposed to have equal frequency ratios. Here is some musical theory that was known to the ancients, and I don't know how many of you recognize that guy. That is Pythagoras, the same guy who had a triangle, and he was very much involved in early music theory, and he or his followers or disciples, or certainly he was certainly in the thick of this, defined what they meant by a perfect fifth. And of course they didn't have pianos then, they were talking about lutes and harps and primitive guitars in those days. But anyway, and probably primitive recorders as well they would have. They defined what they call a perfect fifth, for example C to G on that keyboard, and they decided that a perfect fifth should have a frequency ratio of 3 to 2 or 1.5, and that's what we call 7 semitones in the modern era. And the reason they liked that was that the third harmonic of C would be 3 times the fundamental, would then have the same frequency as the second harmonic of G, second harmonic of the note that's got a fundamental 1.5 times the frequency of the lower note. And so therefore those harmonics didn't beat. When it was perfectly in tune, those 2 harmonics were exactly the same frequency. They didn't beat, and they realized that that actually sounded quite a pleasant pleasant sound. And they probably didn't understand all the reason of talking about harmonics and so on. They just empirically worked out that a frequency ratio of 1.5 sounded really nice. But that's the reason. They were expecting the third harmonic of the lower note to be beatless with the second harmonic of the upper note. The problem is, on a modern piano, a perfect fifth is 7 semitones, and you can work out 2 to the power 7 over 12, and it's just slightly below 1.5. So even if you have a perfectly tuned modern piano, Pythagoras would say, well, that's not really in tune, because the G on a piano is slightly flat compared to where it should be. And of course, this is the problem. Many of you will know this is the problem that is caused by what's called equal temperament. It wasn't always so. Back before the days of Bach, people worked out all sorts of ways of tuning pianos so that some of the perfect intervals that the ancients had worked out could be tuned exactly. But the problem with that was that other intervals were very inaccurate and sounded very out of tune. So around the time of Bach's day, it was realized that the way to do this was to accept that some of these perfect intervals would be a little bit out of tune, and it was acceptable. So let's just have a look at some other examples that the ancients had worked out. A perfect fourth is 5 semitones, and Pythagoras said, well, that's got to have a frequency ratio of 4 to 3 or 1.3333, but on a modern piano it's slightly sharp, 1.3348. 4 semitones is a major third. That corresponds to a frequency ratio of 5 to 4, and again, it's not quite correct. That one is really very much out of tune on a modern piano, even when it's perfectly tuned. In fact, piano technicians use the beats between the harmonics of intervals like thirds and fourths, and listen to the beats, and they know what a perfectly tuned piano should beat at for those particular intervals, and they use that phenomenon to tune the notes on a piano to within 1 hertz. So it's really a very clever way of tuning a piano perfectly by listening to the beats between harmonics. If you've not ever heard that phenomenon, if you ask your piano tuners to demonstrate it next time you get your piano tuned, you'll hear what I mean. So when they're tuning a piano, this is why piano tuners play lots of thirds, lots of fourths, and what they're doing is listening to the beats between the harmonics. And it just sings through. When you know what you're listening for, you can hear it very clearly. So let's have a look at what's inside a modern piano. This is a Steinway D concert grand, and you probably know the basics. A piano consists of a stretched string, and it's fixed to an iron plate at one end with a hitch pin. It's fixed to the iron plate at the other end with a tuning pin, and you turn the tuning pin to adjust the tension. The speaking length is in the middle. The speaking length is between the bridge, which couples the vibrations to the soundboard, and then at the other end on that diagram, the other node is the what it calls an agraph, which is used on high quality pianos for at least some of the notes. It's just a piece of metal with a hole through it to fix the node position precisely, and then the hammer comes up from underneath to hit the string. So on the plan view of the piano, the strings are in the middle of the design. The hitch pin is at the end. Tuning pins are there. The frame is made of cast iron. They paint it gold just to make it look nice and stop it rusting. and there's a bridge, the bridge for the bass strings, and on this piano there's a separate bridge for all the strings that are not on the bass bridge. So the treble bridge is very much longer than the bass bridge. And then the soundboard you can see through the frame, that's made out of spruce. And then the hammers are at the top. You can just see the tops of the highest section of hammers. What I've ringed around there is the top face of hammers that are, when you play a key, those hammers are driven towards the screen from the rear. And then there are dampers over each string. Those stop the vibration when you take your finger off the key. And then the whole thing is contained inside a rim that's made out of a single piece of laminated maple. So let's think about strings. You all probably know the formula for the vibration frequency of a stretched string. I don't need to go through that. L is the length, and M divided by L is the mass per unit length, or the linear density of the string. And I've given a diagram there of various harmonics, and the top diagram of course is the fundamental harmonic, where L is the distance between the bridge and the agraff. So the top note, C8 on a piano, if you work it all out, it's that frequency, and on every piano that note is 5 centimeters long. The top note on a piano and the few below it, they sound the same on every piano that's ever been made, whether it's a cheap piano or an expensive piano. The top few notes all sound the same. The string lengths are always the same, about 5 centimeters. But the difference is in the bottom note, and the bottom note is 27.5 Hertz if you work it out, the bottom note A0, and you can work out from the formula what length it would be if you use the same material as you use for the top note. You just scale it by the frequency, do the sums, and it works out to be 7.72 meters, nearly 7¾ meters. So just remember that distance. It's quite a long distance. There's the formula to remind you. A domestic piano, what I call an artist grand, the smallest piano that a professional pianist would regard as really rewarding to play, is about 6 feet long, and that's 1.85 meters, clearly a lot less than the 7.72 meters that we would like to have. A conventional concert grand, the Steinway D, is 2.74 meters. That's still a lot less than what we might expect. Well, people do actually make bigger pianos than concert grands. Here's an interesting example. This is a piano at a university in Germany. You probably can't easily see how big it is. Unfortunately, they didn't put a person on the picture to indicate scale, but I've ringed around there. That's an entrance door. It's a normal sized entrance door. And the way you play this piano is you go up the stairs there, and the stairs go up to the platform that's about 8 feet above the ground, and you sit there, and the keyboard is then facing you. And if you look carefully, you can see that the longest string starts there at the top and goes right down to the bottom. So the longest string for the lowest A is roughly about 12 feet long on that piano. So that's getting closer than a conventional concert grand. The largest piano I was able to find is actually in New Zealand and is 5.7 meters long. That's a huge long grand piano. It's still less than the 7.72 meters that we would want it to be. So for any piano that's ever been made, we have to increase the linear density for the low notes in order to reduce the length of the lowest note to a manageable value. And the way we do that, and those of you who know pianos will know that the bass strings are basically steel cord, and you can see close up there of bass strings on the left. and they're overwound with copper wire. That increases the mass per unit length. And you can see a close-up of an agraffe there. It's, as you see, it's just a piece of brass screwed into the gold frame, and the string passes through it to make the front end of the string vibration well defined. So that's how we increase the linear density of the strings in the bass. And then on the right, I've got a picture of the treble end of the piano, so you can see that the strings at the treble end are not overwound with copper. Those are just high tensile steel wire. It's the same material that needles are made of. And you can see the bridge at the back. All the strings go over the bridge. And in fact, the treble strings on some pianos don't go through agraffes. The front node is defined by what's called a capo bar. That's just basically a fairly sharp steel edge that also has the job of defining precisely where the speaking length of the string stops at the front. And while we're looking at the treble end, I thought I would point out to you another design improvement that high quality pianos have. Here's a reminder of the side view of the string. And I've pointed out on the right hand photo what's called the rear duplex and the front duplex. Now, duplex means the bit of the string that is either between the bridge and the hitch pin, that's the rear duplex, or between the agraffe, or in this case the capo bar, and the tuning pin. And in the bass strings, you can just see on the left picture that the front duplex, the bit between the agraffe and coming towards you, is going over a piece of felt, and that's just to try to prevent the front part of the string vibrating. You just want the speaking length of the string to vibrate. In the treble, they don't do that. In the front part of the string, there's no felt between the capo bar and what's called the duplex bars, and the bit of the string between the capo bar and the duplex bar is able to vibrate as it wishes. And also the rear duplex from the bridge to the hitch pin is able to vibrate as it wishes. Actually, not quite the hitch pin there, and in the rear duplex there's a duplex bar or duplex plate that defines the vibration length of the rear duplex very precisely. Now, at this point, manufacturers start trying to confuse you with all sorts of technology, and they say, oh well, we tune the duplexes so that the duplexes resonate and they're tuned to precise overtones. I don't know that I believe any of that. I think the advantage here is that by using a duplex design, you're not using felt to quash extra vibrations that go from the bridge towards the hitch pin. Think about the bridge on a piano. It goes up and down as a result of the vibrations of the speaking length. If any of those vibrations are absorbed by felt, then that means that the vibration is having energy taken away from it, so therefore the vibration dies down faster. So by using a duplex design, there's much less energy is taken away into damping felt, and then you probably try to tune those strings so that if they vibrate they're not objectionable. So I think really that's what's going on, and all high quality pianos have duplex bars front and rear. Steinway, I think, probably originated it. Yamaha and Kawai, Mason and Hamlin, Fazioli, Bechstein all use tuned duplexes. This piano has 88 notes, 250 strings. just think about it. That's 20 tons of force across the cast iron frame. That's quite considerable, and it was a technological feat in the 1850s to design a frame that could withstand that sort of force. Let's think about the lowest note. It's on a Steinway D, it's 79¼ inches. Go up the scale, and at the top end of the bass bridge there's a note with strings that are that long, that blue arrow that's just come up, and then the next note up, is that one, which is actually longer. The reason it's longer is that on the Steinway D, the note just above the scale break, as we call it, is not overwound. The note just below the scale break is overwound, so that's where the transition between overwound and non-overwound strings is. And that general arrangement where the bass strings cross over the treble strings is called the overstrung design. And there's the scale break on the Steinway D. The note, the F to the right, upwards as you're looking at it, is above the scale break, and the E below that mark is below the scale break. Virtually all modern pianos are overstrung like that, with bass strings going over the treble strings. There is actually a movement not to use overstrung designs in very big pianos, and Daniel Barenboim has been promoting that actually for the last few years, and one or two very small manufacturers are starting to make what are called straight strung pianos that are not overstrung like that. And in fact, the piano I showed you earlier in the German university was a straight strung design. It remains to be seen whether this is just a sort of fad or whether it will actually prove to be an improvement in design. Let's have a think about the treble strings. In particular, why are there 3 strings per note in the treble? Well, we have to think about the acoustic wave impedance. The acoustic wave impedance is defined as tension divided by velocity, so when you work it out, it works out to be square root of T tension times the linear density. And those of you who know about transmission lines will know that transmission coefficient at a boundary is given by that formula. It's twice the wave impedance of the string divided by wave impedance of the string plus the wave impedance of the soundboard that you're trying to transmit to. That's the standard formula for transmission coefficient. Well, it turns out that the impedance of the string is very much smaller than the impedance of the soundboard, so therefore we can approximate that just to be that formula. And so here's the problem. To keep the acoustic transmission coefficient to the soundboard the same for bass and treble, so the note sounds the same volume in the bass as it does in the treble, I need to keep the string impedance, or T multiplied by linear density, the same. Otherwise it's going to vary across the scale of the piano. So that's the condition. I need to keep the tension times the linear density the same, but we're going to keep the tension roughly constant per string, otherwise the tone quality changes. But we've just decided that we want to have a linear density that's much larger in the bass. So how can we square that with saying that I want to keep the string acoustic impedance the same when the linear density is going to be much larger in the bass? We've got to do something to keep the string impedance the same in the bass and the treble, and this is how we do it. The lowest note we just decided should be 304 inches. It's actually 79¼ inches on a Steinway concert grand. There's the formula for the frequency. So if the tension is constant, the linear density has to be increased, and you can just put the numbers in. It turns out to be nearly 15 times in the bass. The numbers work out even worse in a smaller piano, but it's closest to being ideal in a large concert grand. There's the formula for the impedance of the string. So the bass string impedance is increased by the square root of 14.7, which works out to be 3.8 times over a single treble string. So in the treble we use 3 strings. That increases the total linear density for all 3 strings. That increases that by 3 times, and also the 3 strings all have the same tension, so the tension is increased by 3 times. So you multiply those 2 together, take the square root, and the string impedance has increased by 3 times in the treble by using 3 strings. Now what you're all saying is, but why don't we have 4 strings in the treble? Because that would be closer to 3.8, which is what we need. And I think the answer to that one is that most manufacturers have decided that 3 strings per note in the treble is just enough, and we can't really complicate things anymore by having 4 strings per note. That would just be too much. Although there are some manufacturers, there are a few manufacturers who make pianos with 4 strings per note in the treble. Just an aside, which I'm not going into here, if there are 3 strings per note, that's 3 coupled resonators, so there are 6 normal modes. And it's quite interesting to think about which normal modes of those 3 strings are excited by a hammer hitting from one side. And there's a whole issue of philosophy surrounding that. Let's think about harmonics. We all know what a harmonic series is: fundamental, second, third, fourth, and so on harmonics. Those are fixed by the guy called Fourier in France, who worked out that the harmonics had to be in ratios of 2, 3, 4 and so on, integer ratios. If we try and translate those into musical terms, then a very low C turns out to have those notes as its harmonics, but some of them are very out of tune because music notation kind of is fixed, but the harmonic frequencies just don't happen to fit some musical notation very exactly. And in particular, the 7th harmonic and the 11th harmonic are very, very out of tune. We're not so worried about the 13th harmonic because there's such high harmonics, there probably isn't very much of those, but certainly the 7th harmonic is nasty, and the 11th harmonic is nasty. So manufacturers know about that as well, and so traditionally on a piano, the strike point, that's where the hammer hits, it's at 1/8 of the string length. So there's that distance from the hammer to the agraff is 1/8 of the total distance from the bridge to the agraff. And the point of doing that is it gets the nicest tone quality because it minimizes the out of tune harmonics by doing that. Minimizes the 7th and the 11th harmonics. So what do you do when you're laying out a piano, when you're designing a piano? The strike line, that's the line of all the hammers, is traditionally a straight line, and in the Steinway piano it's that straight line. You can't see the hammers at the lower end because they're obscured by the dampers, but that's where the strike line is. And then the front node line I've drawn in blue there. That follows the capo bar to start with, and then it ends up following the line of the agraffs. And then the treble bridge defines the rear end of the speaking length, and if you look carefully you can see that every string has 7 times the length between the strike point and the treble bridge compared to the distance between the strike point and the front node line. So if you look at the front of a piano, you can tell exactly what the shape of the bridges is. And the same is true of the bass end. There's the bass bridge, and there's the front node line following the line of the agraphs at the front, and again the bass bridge is exactly 7 times further away from the strike point than is the front node line. And what's interesting is that in very small pianos, this doesn't apply to the Steinway, but in very small pianos you'll see that the treble bridge curves back a bit. They call that a hockey stick design, and the reason for that is in a small piano there isn't the room to do what Steinway did and just extend the treble bridge back in almost a straight line at that end. In a small piano the treble bridge will curve around like that. The advantage of that is that the notes a little bit above the strike point to some extent are longer than you might otherwise expect, and so they sound fuller, they have better sound quality, but the disadvantage is that the note right at the scale break does not sound as good as you might expect. Steinway didn't make that design compromise. They were designing a concert grand and didn't want to compromise the quality of the sound from the treble bridge. But what's interesting is that they did hockey stick the bass bridge. So on a Steinway, the notes a few strings above the lowest note sound more resonant than you might otherwise expect, and then the very lowest note is not quite sounding as you might expect, judging from the original notes, a few notes above the lowest note. And there are other approaches. Steingraber, for example, a German manufacturer, makes the bass bridge completely straight, and then the notes change their sound very much more gradually, but the notes in the middle of the bass bridge are not as resonant as you might expect. Steel wire doesn't bend easily, so that means the highest harmonics have extra restoring force. That means that the high harmonics have increased frequency, and it's worst for the fat strings. And that's why small pianos sound bad. They have a very high linear density, fat bass strings. That means the sound isn't very good. And big pianos have thinner bass strings, gives you better sound. And we can quantify it. You can measure the harmonic frequencies from a fundamental note, 261 Hertz, and you can see that there's a difference. As the harmonics increase, the difference away from ideal gets larger and larger, and each octave is traditionally tuned to be beatless with the second harmonic of the note 1 octave lower. So in fact an octave on a piano is not twice the frequency, it's actually larger, slightly a little bit larger than twice the frequency of the fundamental. So we call that octave stretching. The octave intervals on a piano get progressively sharp as you play up towards the top of a piano. A pipe organ is almost perfect acoustically, and that means that we can't tune a piano accurately to a pipe organ. And the deviation from ideal is called the Railsback curve, and there's the Railsback curve for a typical piano. The average is the green curve, and the actual data is the rather noisy grey curve behind it. So that shows when you measure the frequency accurately, pianos are only really close to perfect over the middle part of the range and up to the top treble. They're deviating away. The frequency is getting very sharp. Down at the bottom, they're getting very flat. Musicians like drawing diagrams like this of harmonics. We've seen that before. Here's a typical music book showing the difference between a soft note and a loud note. And I think musicians very often think that's precisely what strings do in a piano. Well, engineers know better. You probably know the wave equation if you've studied any amount of physics in college. That's a partial differential equation that tells us how much the wave displacement changes as a function of time and distance. And we know that the speed is given by that formula C. And the precise shape of the string vibration you get by solving that wave equation. And at this point I want to stop sharing and show you an Excel spreadsheet that shows you exactly what the solution to that 1D wave equation is. So I'm going to stop sharing and then share differently this. So this is ordinary Excel straight out of the box. I want to emphasize there are no add-ons at all in this. Excel is actually very, very flexible, and you can program Excel to solve the 1D partial differential equation, the wave equation. And what I've programmed it to do here is to respond to a hit from a hammer 1/8 of the distance away from one end of the string. So this is exactly like what's happening in a piano. And this Excel program is now going to solve the wave equation in real time for you. So what happens is that displacement starts to propagate out at the speed of the wave in the string. Now I don't believe all the very high frequency ripple on that picture. Those are Fresnel ripples just caused by the fact that it's a finite sampling solution. So ignore that, but what's important is that it doesn't look like a sine wave at all. What's happening is that the disturbance is traveling away from the original hit point, and it's traveling in both directions. And here's a question for you. What do you think happens when the disturbance hits one end? This will be the agraph end, the front end of the string. What happens? Well, let's see what the wave equation does. It reflects back, and it reflects back in antiphase, so therefore the disturbance at the agraph end is now 0. So what is going to happen is that this disturbance that you can see is roughly a square displacement, and of course the length is 1/4 of the string, because the original strike point was 1/8 from one end of the string. So that is going to travel all the way down the string. This takes a bit of time to get there. You might want to consider what you think is going to happen when this disturbance hits the other end. Let's see what happens and see whether you guessed right. So what is going to happen is the disturbance is again reflected in antiphase. So what we get at one critical time is the original disturbance, but it's in the opposite direction. And again, it's 1/8 of the end from 1/8 of the string length from the end of the string. And then, of course, once it's reconstituted that, the same thing happens all in reverse. It starts traveling back towards the front end. So again we have this sort of flat-topped disturbance. It's now traveling back, but it's negative now, and it will hit the front end eventually, and then of course when it hits the front end it will be reflected in antiphase, and if we just hit this at the right time we find that the original disturbance is recreated, and then of course it just carries on infinitely. So that's the last thing that I wanted to show you, so I'm going to stop that and go back to my presentation. So in conclusion, pianos didn't just happen. There's been a great deal of engineering thought gone into piano designs. This was high tech in the 1850s to 1900s. Pianos were the first example of a real high-tech product, precision manufactured, and the spin-offs were enormous, including wood technology, steel wire, precision steel wire, precision mass production. There are still innovations being made today by the top manufacturers, and the top manufacturers are still researching how to make pianos better and to sound better. So that's my talk. Thank you very much indeed for your attention. I will hand back to our moderator.
Thank you very much, Dr. Clive, and I think it was an interesting topic, and you covered almost many aspects of engineering and physics of pianos. Right, so we have few questions coming up. Shall I read them out to you, Dr. Clive?
Yeah.
Okay. Let me see. Yeah. The first question, I have seen musicians tuning a guitar. Is tuning a piano is something similar? And during each concert, are the artists doing or supposed to do tuning? It's a general question for you.
Yeah, I'm not quite sure of the question here. Guitars are tuned. I don't know that guitar is tuned beatless. They would generally tune so that the intervals sound correct. I'm not sure about whether you mean should they be tuning a piano during a concert or tuning a guitar during a concert.
Like, yeah, he's asking, I think, do we have to tune a guitar before every concert or like before you playing? Sorry, a piano.
Well, I'm not a
Asking about
guitarist,
piano.
so I don't know.
No,
Uh,
he's asking about pianos.
Yeah, I mean, certainly, actually, pianos do not stay perfectly in tune very long. A piano in good order, a concert piano, um, probably would stay in tune for about a couple of hours, which is the length of one concert. And it's certainly possible to hear slight imperfections after that sort of time. So, I mean, not enough that you would want to get it tuned again if it's in a domestic setting, but in big name recording sessions, for example, where you can't have any possibility of notes being out of tune, there's always a piano tuner around on call so that they can tune odd notes as they go out of tune throughout the session.
And Dr. Clive, one more question. I'm sure we have answered it through the session itself. Like, what happens when a piano pedal is pressed?
Yeah, so there are three pedals on a grand piano. The right hand pedal, sorry, I'm getting some feedback from occasionally. The right hand pedal lifts the dampers so that if you press any notes, then the sound keeps on going after you lift your finger off the key. The left-hand pedal has different functions on upright and grand pianos. On a grand piano, it shifts the keyboard to the right, and there's a huge controversy over precisely what that does to the sound. What you will read in textbooks is that therefore one string or two strings out of the three is hit and the other one isn't. That's actually not what happens. And the precise description of what's going on there is quite interesting. The middle pedal has a rather strange function. If you press the middle pedal down, then it keeps up dampers that are already raised because you've got your fingers on the keys, but it has no effect on dampers that you didn't have raised because you didn't have your fingers on those keys. Middle pedal is almost never used by many pianists. I mean, I've used it once in my career, and really only so that I could say I'd used it. There is some repertoire where it's required to be used. I'm not denying that, but it's very much less used than the other pedals.
And there's another question. It's related to the violin. If you can answer, I'll read it out to you.
Yeah, on the violin, harmonics tend to be flat
On the
rather than
violin,
sharp.
yeah.
I'm not a violinist. I can't offhand think of a particular reason why that would be so on a violin. I'm kind of wondering whether it's due to well, the string elasticity would still tend to make the harmonics sharp, wouldn't it? Yeah, I'd need to think about that one. I'm not a violinist.
And thank you, Dr. Woods. And I think there are many requests if you can share the presentation on the Excel sheet for the benefit of students. Maybe if you like, you can share it with us and we can share it with the
Okay,
participants.
sure.
Yeah. Is there any questions from the participants? You can direct it into the chat again. And yeah, I think for the moment, the questions are that. Thank you very much, Dr. Clive, for patiently answering all
Thank you.
the cues coming up. And now, as next, I would like to invite Professor Jennifer De La Cruz, the Student Activities Committee Chair of IEEE Region 10, to deliver the closing remarks and the vote of thanks for the session. Prof. Jen, over to you.
Hi, good morning, good afternoon, everyone, especially to our dear speaker, Dr. Clive Woods, all the participants in and outside Region 10, and the vibrant organizers of R10 Talk webinar series. It was a morning of interactive and insightful session about physics and engineering of pianos. And I would not have known most of the facts if I missed this webinar. So my daughter loves to play piano and guitar. We are awed by the acoustic sounds produced by these instruments, as well as its physical and technical evolution. Modern technology has influenced its intricate designs from a traditional soundboard to electromagnetic pickups. So we also get to relate our basic knowledge of physics, transmission lines, to our love of music. I mean, adjusting strings, its impedances, and producing different harmonics, that's very cool. It was incredibly an interesting talk, and personally, I have loads of takeaway. Next slide, please. So on behalf of R10 Talk Director, Professor Lance Fung, and R10 Talk team led by Dr. Zia Ahmed, we thank you for your time and effort. We appreciate your support to Region 10, and we are truly grateful, Dr. Clive, for sharing your distinguished engineering expertise to R10. And I also would like to thank Dr. Anjali, who is here, for initiating the invitation to you as our speaker for today. Thank you very much, Dr. Clive.
Thank you very much.
And we also thank our dear Ms. Waronica Hipola, our region student representative, for moderating the 14th session of R10 Talk. Thank you, Ms. Waronica. Over to you now.
Thank you, Prof. Jen, for that kind vote of thanks. And yeah, so now we have come to the end of our session. So before we close up, let me remind you a few things, and then we will take a group photo with the panelists and we can end the session. So if you have any feedback, and we would like to hear from you how you felt about this session, and we can improve our future sessions as well. So please give your feedback at this. If you scan this QR code, you will be directed to the Google form where you can give your feedback. And later, I will also put the link in the chat box before we leave. So please give your honest feedback so that we can improve in the future. And also, I would like to thank all the committees of IEEE Region 10 for initiating these and working hard towards the success of R10 Talk so far. So all of these combined make a great effort which led to the successful initiative to come to this much of episodes. Even in 2023 we have completed now 14 talks. So thank you very much all the teams and the volunteers who work here in these committees. So thank you very much, and we hope that you will connect with us with our LinkedIn, Facebook, and YouTube channels in the future, and also in the you can see all our past or previous webinars which are like posted on our YouTube channel. And in the future, if you are interested, you can join with us in our Facebook live streaming of all these webinars, and you can know about them from our social media. Thank you very much for your active participation. And so once again, for the recordings of the previous sessions, you can join our YouTube channel. So before closing up, I would like to invite all the panelists to switch on their cameras to take a group photo. Thank you very much. I will be taking one from my side, and maybe Hisham can help me to take another one. Thank you. Professor Lance, are you in a position to switch on your camera? Maybe let's take a photo. Okay. Give me 1 minute. In the count of 3, I'll take one. 1, 2, 3. Thank you very much. I think Hisham, you also good.
Yes.
Thank you very much, everyone. Thank you.
Thank you.
See you again.
See you again.
Thank you very much.
Thank you. Thank you very much. Thank you.
Thank you.